So for this problem, we have a mounting bracket with our given dimensions in the diagram that is subjected to a 700 Newton load at point C and 350 Newton reaction forces at point A and point E. And we're tasked with determining all of the internal forces and moments at points B and point C. So the first step in solving this problem is to determine the internal forces and moments we want to solve for. So I'm going to break it down, and we're going to start at point B. So at point B, we're going to have forces in the y direction, in the x direction, and in the z direction. And we're also going to have moments about each of those axes as well. So we'll have a moment about the x-axis, a moment about the y-axis, and about the z-axis. So our next step in solving this problem is going to be to utilize our equilibrium equations to solve for the values of each of these forces and moments. So we'll start with summing all of the forces in the x direction at point B. So at point B, we have Fb of x, and that is all. And of course, this is going to all be equal to 0. We'll follow a similar process for the forces in the y direction. And the forces in the y direction, we have our force at B and our 350 Newton force. So we have our Fb of y plus our 350 newtons, and that is all going to be equal to 0. Same process again for the forces in the z direction, and all we have is Fb at z, and that again is going to be equal to 0. So now that we've solved for all of our forces, we can then figure out that all of our forces in the x direction are 0, so Fb of x is 0. Same thing here, Fb of z is 0, and solving for Fb of y by rearranging this equilibrium equation, we find that Fb of y is equal to negative 350 newtons. All right, our next step in this is going to be to solve for our moments. So for summing the moments at point B in the x direction, we're going to have our m of x, and we're going to subtract our 350 Newton force acting 0.25 meters away from our point of interest. And again, that's going to be equal to 0. For summing our moments in the y direction, we're going to have m of y. We have no forces to cause a resultant moment, so that's, again, the equilibrium equation is going to be equal to 0. And we have the same scenario in z, and we have m of z, and that is all going to be equal to 0. So now we can solve for m of x by rearranging this equation, and we find that m of x is equal to 87.5 Newton meters. Now that we have solved for all of our forces and moments, we can draw our final answers on our solution diagram. So from what we solved before, all we had was a force at B in the y direction, which was negative 350 newtons. So we can draw a downward arrow that says 350 newtons. And we also found that we had a moment about the x-axis, which was 87.5 Newton meters. So about this x-axis, we have 87.5 Newton meters. And that is our final solution for all of the forces and moments acting at point B. So just to recap, we had our force at y, and then we had our moment about the x. Our next step is going to be following the same process that we did at point B, but this time at point C. So we're going to do the same thing that we did for point B, but this time our point C acting at this point, we're going to have forces again in the y direction, in the x direction, and also in the z direction. And similarly, we're going to have moments about each of those axes as well. X, y, and z. So now, like we did with point B, we're going to use our equilibrium equations to solve for the values of these forces and moments. So summing in the x direction, we have our Fc of x, and since we don't have any others, that's just going to be equal to 0. Same process in the y direction. We have our Fc of y, and our 350 Newton force. And that, again, is all going to be equal to 0. Do the same thing for our forces in the z direction. And all we have is our Fc of z, and again, equal to 0. So now we can solve for Fc of y by rearranging this equilibrium equation, and we get negative 350 newtons. And now we'll follow again the same process, but summing the moments in the x direction. So we're going to have our moment at x, and then subtract our 350 Newton force that's acting at 0.25 meters away, and that all equals 0. In the y direction, we just have m of y, and equilibrium, that's going to be equal to 0. And then in our z direction, we have our m of z, and we also have our 350 Newton force, but this time it's going to act 0.3 meters away from our point of interest, and again, that is all equal to 0. So here we can solve for our m of x by rearranging this equation, and that's going to be equal to 87.5 Newton meters. We have m of y equals 0, and we can solve for m of z here, and that is going to be equal to 105 Newton meters. So now that we've found all of our unknowns, we're going to go ahead and draw our moments and forces. So we have in the y direction, our Fc of y was equal to negative 350 newtons. So we'll draw a downwards arrow. 350 newtons. And then we found we had a moment about the x-axis and a moment about the z. So about the x-axis, we have m of x equals 87.5 Newton meters. And then about the z-axis, we have m of z is equal to 105 Newton meters. And now we've solved for all of our internal forces and moments at point B and at point C.